Today's lesson is on section 8.6, write and graph exponential decay functions. So far up to this point in this chapter, we've been working with exponents, and then in the most recent section, 8.5, we worked with exponential growth functions. And what happened in exponential growth functions? We pointed out a few things that we want to keep an eye on when these kind of functions come about. One thing is that they start growing very slowly, and then all of a sudden, as they hit a certain point, they start growing, and then all of a sudden, they pick up their pace and increase very rapidly. And that's usually how something with exponential growth will go. Again, we talked about maybe technology, new technology that comes out. Again, it starts off maybe only a few people have it, but then after a while, that'd be represented down here. But as soon as it becomes mainstream, then everybody gets one. It becomes very, very popular. New technology has a way of doing that very often. Also, populations can grow exponentially. So we talked about some examples of things that can grow or have exponential growth. We modeled these equations with this form, y equals a times b to the x power. And we talked about how to make one of those equations if we have a table as well. There's usually, just like when we did linear equations and made some kind of, could find like the slope and the y-intercept from the table, same thing here with exponential growth equations as well. There's some kind of pattern going on in my y values as the x values go up by 1 every time. The y values are some kind of pattern here as well. In an exponential growth pattern, we saw that it was going to multiply by some number. Like in this case, it's multiplying by 3 every time in this equation, or sorry, in this table. So to make our equation, then that usually showed up as our b, which is our growth factor. And our y-intercept is just like, kind of like with linear equations when you plug in 0. Well, in this case we get 2. That's usually what number will show up in place of a in our exponential equation. So this equation ends up looking like 2 times 3 to the x power. And if I put those values in, I would find out that, yeah, that's the equation that would make that table work. Y equals 2 times 3 to the x power. So this is an exponential growth equation. Today, the new section here, 8.6, is talking about exponential decay. And obviously, if we're talking about growth, we're talking about something growing, getting larger. Decay is obviously kind of the opposite of that, going the other direction. Something that's decaying, we're getting smaller and smaller, or it's fading away. An exponential growth equation, how does it compare to exponential decay? It's actually just the mirror of an exponential growth function. So again, something that starts off maybe up here somewhere in my graph, and then it'll get slowly closer, closer, and closer. We talked about how it gets closer to the x-axis, but never actually touches it. But something that's kind of showing decay has one of these kind of patterns. It decreases rapidly maybe at this point, and then at some point it has this kind of decrease here, some kind of percent decrease where it decreases by 80% every time, or 70%, or it's going down so much all the time. Not like a linear pattern where it just goes down a certain amount every single unit we're talking about, but just a percentage of that every time. And that's what kind of gives it this flattened out shape that it has here for an exponential decay. In terms of a table, what would this look like, or what would happen then in a table for exponential decay? Well, exponential growth, we talked about how the pattern we see is it's multiplying every time to find what the next value is in our y-coordinate. So what do you know, in exponential decay, again, similar but just the opposite in this case because we're going the other direction. Exponential decay, we're going to find that our numbers are typically dividing by something to get to the next number every time. And so I have a similar table here, but just notice the numbers are going the other direction, correct? So you can see that the pattern in this case is we are dividing by 3 every time to get to the next number. Dividing by 3. Dividing by 3. Well, the nice thing about exponential decay functions is they still follow the same form of the equation. Y equals a times b to the x. And a is still kind of like a y-intercept. When I put 0 in for x, it's what I get. So this one also would still look like y equals 2 times. But now instead of having a growth factor, we have a decay factor, some number that again is continuing the pattern. Well, how's that happening in this problem? Again, we talk about it's dividing by 3. So I'll usually ask the class, and usually if a little bit of thinking, they can come up with, well, how can I make it divide by 3 every time? What would have to be for that to happen? Is as opposed to having 3 like I did with the exponential growth, in exponential decay, I need 1/3 to be whatever b is in this case. And that's going to make then my values get divided by 3 every time I increase the value of x. It's going to keep this pattern going here, which is what we see when we have exponential decay. So just like I did with exponential growth functions, I pointed out a few things that I want students to keep in mind when they're things that happen when they see exponential growth functions. Same thing here with exponential decay. I've got top 3 things I want you to take away. I mean, there are many things you can take away, but here are top three things I would definitely want you to know after learning about exponential decay functions, what you should know about them. Again, they set up like exponential equations. All exponential equations have that kind of same form, roughly, but to be an exponential decay function, we need b to be a value between 0 and 1. That's what's going to make it always decrease the value of y as we increase x. Like as I keep plugging in bigger and bigger numbers here for x, what will make this be an exponential decay function where our population or our money amount or whatever it is, as time goes on, what will make it go down is this value of b has to be something in between 0 and 1. Because again, it's almost like taking a percent of that number every time, and that's what's making it decrease. The second most important thing I'd say that you should know about exponential decay functions is as x increases, the graph will get closer and closer to the x-axis, but will never actually touch the x-axis. Again, something we talked about with exponential growth functions as well. And just cutting back to our graph here to show that quickly. Again, right here, as we get farther and farther up the x-axis here, we're noticing it's going to get closer and closer. This line will get closer and closer to the x-axis, but it'll never actually get to it. Because again, this number that we have here, as I'll talk about in class, this number here, as we make it smaller and smaller, as x gets bigger and bigger for it, this number will become a smaller and smaller fraction, but it'll never actually be 0. And so since that number can never actually be 0, well, we can't have 0 for an answer than for y. So as we talk about here, as x gets bigger, it'll just make that factor, that b portion of our exponential equation, it'll make that a smaller and smaller fraction, but it'll never actually get to 0. It'll be, at some one point it'll be like 1 over 1,000, then it'll be 1 over a million, then it can be, that fraction could be 1 over 2 million. Like, it could get bigger and bigger, like in terms of fraction, that denominator will. And so that number will get closer and closer to 0, but it'll never actually get to 0. And so that's why we say it gets infinitely closer to the x-axis, but will never reach it. As students go on, again, you guys will run into topics like this more and more where we talk about things tending towards infinity or limits. That's things you'll cover more in high school as well. And this is kind of one small example of that right now here, even in intermediate algebra, something we see. And it's a tough concept to grasp, but once you get better at seeing it and seeing it more and more, then you'll understand it better too. But exponentials is one place we see it. And then number 3, one more to talk about, is I'd also like you to remember that like an exponential growth function, like the ones we did before in section 8.5, a is often like our initial amount or our y-intercept. And this will especially be helpful in word problems too when we're talking about some kind of population starting off and then maybe it has an exponential decay pattern. That a is often like our initial amount, like where we start at. And then the population maybe starts decreasing, or again, it may be amount of money and something that a value of something that depreciates. So then that a is usually like our initial amount we can plug in, and then b will be like our decay factor, and we'll figure out after how much time what the new value of that product or that money amount or population, what that new value is. But often in these word problems, a is going to be kind of like an initial amount for us. Going through just an example too here of writing a rule for an exponential decay function. Again, it's going to have some form like this, just like the exponential growth functions did. So again, that's one nice thing. This a, again, kind of like a y-intercept. Very often, unless we've shifted the graph somehow, it's like often like our y-intercept. And this b is often like our decay factor. We had growth factor for when we had section 8.5, we talked about growth equations. Well, now it's our decay factor because we're talking about exponential decay equations. And we can figure out both these things just by looking at our table. So looking at an example like this first one. Again, what's happening to my y values as I keep going? Well, I see a pattern. It's going down. The numbers are going down. It's not subtracting every time because that'd be a linear pattern. But numbers are getting smaller every time. From 32 to 4. And then 4 down to a half. And again, sometimes in these fractions, it's a little tough to tell. But definitely starting at these first 2 numbers, you can figure out what the factor is. It looks like it's dividing by 8. So what will make that happen? in an exponential decay equation is that my b is going to be 1/8. That's what will make that happen in one of these types of equations. My y-intercept, my value for a is going to be, when I plug in 0, I get 1/2. So that's what a will be. So my equation is going to be y equals 1/2 times 1/8, and that to the x power. And I typically put the factor, the k factor, in parentheses like this, just because you'll often see it in that form. And especially if it's a fraction, you just want to make sure they realize that this is what it should look like, 1/8 to the x power, and not maybe just like I got up here, maybe just 1 to the, like just a 1 to the x power, or that top number to the x power. You want to make sure that they understand it's the whole fraction there to the x power. So that's why I'll typically put in parentheses, which I think is a good move. So I would get in the habit of doing that as well. Looking at this next one here. Again, there's some kind of pattern going on with the y coordinates. If I look at those carefully, I can see they're going down again, but again, not like subtracting the same thing every time. It looks like they're dividing by some factor. I would say that factor is probably going to be 3. So how can I make that happen in this? In an exponential decay equation, my b is going to be 1/3. That's what's going to make it decrease by 1/3 every time, or divide the y coordinate by 3 every time as I go up in my x coordinates. So y equals my y-intercept, my a, looks like it's going to be 9 in this case. So 9 times 1/3 to the x power. So again, those often just like putting together exponential growth functions. But now if we see the dividing pattern, we know it's going to be a decay function instead. So b is going to be some number between 0 and 1. Then just like I did for exponential growth, I'll give one example here of an exponential decay equation and how to graph that. For exponential decay, you can plug in, again, numbers like -2 and -1 for x, but I think sometimes it makes a little more sense just maybe just to start at 0 and start plugging in numbers from there. And you can go up by 1s, or actually sometimes going up by 2s or 3s actually makes it a little easier to really see the shape of the exponential decay equation. So, but I like to start at 0 just because, again, in a problem, if we get a problem with exponential decay, it's probably because we're starting off at 0 and then something's decaying from that point and decreasing. So I usually like to start there, and then I think it makes a little more sense for many of our problems. So for this one, I'm going to start at plugging in 0 first. So y equals 10 times, well, 1/2 to the x power. Well, in this case, if that's 0, well, that means 1/2 would be anything to the 0 power is just 1. 10 times 1 would just give me 10. So 0, 10, my first point. If I plug in 1, nice thing about having 1/2 as my growth factor, or in this case, I guess decay factor, sorry. Nice thing about having 1/2 as my decay factors, it means I'm just going to take half of the previous number every time. So if I put 1/2 to the first power, it's just a half, times 10 gives me 5. And then if I just keep that pattern going, half of 5 is 2.5, half of 2.5 is 1.25, and half of 1.25 would be 1.625. So I can get my numbers there, and again, I will get some decimals. That's almost unavoidable here in these kinds of problems, and that's fine. So I can still plot these and make a decent graph. And again, we kind of got the idea now that we know what the decay equation is going to look like. It's going to get closer and closer to the x-axis, so we can kind of expect that too. 0, 10 would be right up here. 1, 5, 2, 2.5, 3, 1.25, 4, 6.25. Already I'm under 1 here. Again, I can start to get even the idea. If I put in a few more points, I can get even closer to the x-axis and what it would look like. But I can kind of see that here's what it's going to look like for my graph. I'm getting closer to hitting those points, but the line's going to get closer and closer to the x-axis. Again, I'll kind of show by flattening out really along that x-axis. But really, I know that it's infinitely going to get closer and closer to it, but never actually get to it as it keeps going there. So there's an example of what the exponential decay functions look like and how we can work with them. Again, similar to the exponential growth. These some things we can do similar to that concept. But exponential decay, we're starting off with some number and decreasing from there, and that's what our equation will do.